Alright y'all, today we are going to talk about polynomial modeling. What is polynomial modeling? Well, it's applications, right, or creating models where we create polynomial functions to represent something that's happening in the real world. So I'm going to start off with an example from the lab manual, but I'm actually not going to use the lab manual pages. I'm going to write it in our notes so that we have plenty of space to write as much as we need to. So I'm just going to go ahead and write up here problems. These problems are from the lab manual section, polynomial modeling. The first one that I would like to talk about is number 5. I'm going to copy it here really quickly. So we have a woman who is creating a garden, and 3 of the sides of the garden are going to be fenced in. We have 100 feet of fencing for that. And then the last side of the garden will be the house. So we won't cover that side in fencing. Our first question is to write a function that models the area of the garden. So the first thing we want to do is to identify the things that we're going to need to solve this problem, right? There's a lot of information that we're given. What do we need to know? So definitely important that we have a rectangular garden, right? So we're going to be dealing with a rectangle. Also very important that we have 100 feet of fencing. And that 100 feet of fencing is going to cover 3 sides, right? And then we have the house as the 4th. So we don't need it for the 4th. Then what are we looking to do? We are looking to model the area of the garden. That's all of the information that we need to look for. As we usually do with application problems, right, word problems, let's go ahead and make sure that we understand what the points are going to look like for this problem. So let's think about it really quickly. We're asked to write a function that models the area. So if we're trying to model the area, that's definitely going to be the dependent variable, right? That's going to be our output. And I'm going to call that big A. I just decided to use big A. You could have decided something else. So this is the area. And we're not quite sure what exactly the independent variable is going to be. So let's kind of hold off on figuring out what we have here. All right, so we're not given any variables or anything, so this is kind of all we know for now. Let's continue to gather information and sort of organize it in a way that helps us kind of make sense of what's happening. The next thing that would probably be helpful is maybe a picture, right? A diagram. So again, we have the house on one side. So this is the house. And then we have the garden situation happening. It's a rectangle. So something like this. What are these sides going to look like? Well, we can name them whatever we want to. So maybe let's say X and Y, and do we need a third name for this one? We actually don't, right? Because this side, since it's a rectangle, is going to be the same length as this side, right? So this is another X over here. All right, what else do we know? So we've used the fact that it's a rectangle. We've used the fact that we have 3 sides with the house as the 4th. The last thing that we have yet to use is the 100 feet of fencing. So this is all the fencing, right? This part, this part, this part, if we know we have 100 feet of fencing, then that means that this length here, right, from there to there, is going to be 100 feet. So we know a few things so far. So that's a diagram. Again, we're looking to model the area. What can we say about the area of this rectangle? Can we calculate it with what we've been given so far? Yeah, well, we know that the area of a rectangle is the length times the width, right? So we have x and y. So A equals x times y. We know we can't really solve an equation that has this many variables, right? We want to have an independent and a dependent, so we need to get rid of one of these two. The only way we're going to be able to do that is to figure out what one of these variables is in terms of the other. So let's see if we can figure out any more information from this diagram. We know that the entire length of fencing is 100 feet, right? So what can we say about that? How can we say that mathematically? That means that 100 is equal to this length, which is x and y and x. So that length mathematically is length x plus length y plus length x. So x plus y plus x. Let's combine like terms here. So we have 100 equals 2x plus y. Well, we said we wanted to figure out what one of these variables was in terms of the other. We can do that just by solving this equation for one of these variables. So which one is going to be easier to solve for? Probably y, right? Because it's already got a coefficient of 1. What do we need to do to solve for y? We just subtract 2x to the other side, right? So y is 100 minus 2x. Now, if y is equal to 100 minus 2x, then that means that we can replace y here, right, with 100 minus 2x. So we have area equals x times 100 minus 2x. Now this is a function that models the area of the garden. Let's go ahead and come back to our independent and dependent variable thing here. Now we do have one variable on this side, and this is our independent variable, x. What does x represent? Well, x is the length of the garden, right? Side length of the garden. Side length. And what are the units here? So the side length, we're talking in terms of feet, so we have units of feet, which means that our area is going to have units of square feet. The answer to this part A, the function that models the area, is A equals x times 100 minus 2x. The second part of the question is, what is the domain of the function? Okay, well, we've talked about domain before plenty of times, right? In the context of word problems. So this is asking us, what are all of the possible values for our independent variable, right? Domain is the collection of all possible input values, right? Input, independent. So what are our possible x values here? What are the possible side lengths of this garden? Well, let's look at a couple of examples. So if I've got, let's say we have, I don't know, 30. Just throwing something out there. If this side is 30, then this side is 30. which means that this side here must be, well, we've used up 60 feet of fencing, which means that there's, out of 100, 40 left. Right? What if I made this length 60? Well, then that would mean that this side would have to be 60, which would mean that we've used up 120 feet of fencing. So how long is this part? This is not possible, right? We only have 100 feet of fencing, so we can't have that situation. So what is the maximum? What is the longest, even though it would look ridiculous, what is the longest our garden could be? Well, right, we tried 60, that was too long. What if we try 50? If I have 50 on both sides, that means that I have how much left for this part, right? This is 100. We have 100 feet total of fencing, so this is 0 feet. That doesn't work either, right? Because that 0, right, doesn't leave us a rectangle, it's just a line where the two sides of the fence are backed up against each other. So that's not really a garden. But anything less than 50 works, right? Might look crazy, but even if we have like 49 or something, right? 49 feet and 49 feet, that leaves 2 feet here. It looks ridiculous, but it's possible. So anything less than 50 is fine. And then of course we need to be larger than 0, right? We can't have negative domain. So the domain for our function is 0 to 50. Those are all of the possible values for x. Okay, third question. Determine the dimensions of the garden that maximize the area. All right, so here we're definitely looking for dimensions. And what's the key word? Maximize, right? Let's take a quick look at our area function. So our area function has two x's. When we have two x's and they're both a part of factors, what does that mean? It means we have a quadratic, right? When we have a quadratic and we see the word maximize, we want to always think immediately vertex. So we're definitely going to want to find the vertex of this function. How do we do that? We find h using negative b over 2a, right? Can we see what b and a are here? Nope, we need to put this into standard form, so let's go ahead and do that. So I'm going to bring this down. X times 100 minus 2x. Standard form here means we need to multiply, right, or distribute means we need to distribute. So distribute x to that term and that term. We have 100x minus 2x squared. If we want to, we can rewrite that really in standard form where we have the decreasing terms, plus 100x. So here we see that this is a, this is b, right? Because those are the terms attached to the x squared and the x, respectively. So then that means that h is negative 100 over 2 times negative 2, which means that we get an h value of negative 100 divided by negative 4 is 25. What is this? Well, h is our input variable for our vertex, right? So that means that this is the x value x value, which is the side length that maximizes, that gives maximum area. Well, what are we looking for? We're looking for the dimensions, right? So dimensions means the side length x and the side length y that are going to give us the maximum area. So we have the side length x, that's 25 feet. And then we need to look for the y part. So how can we find y given x? Well, we could go back and sort of think it through and write out the equation and solve everything again. Or we can remember that we actually already found y in terms of x, right? We know that x is 25. We can easily find y just by using this equation. So we know y equals 100 minus 2x. X is 25, so we have 100 minus 2 times 25, which is 100 minus 50, which is 50. That's our y value. So we have 50 feet, and our dimensions are 25 by 50 feet. That will give us the maximum area. I am going to give y'all some steps for polynomial modeling that are good guidelines. Again, I said guidelines, not every problem is the same and not every problem will have the same requirements, but these are generally kind of good to follow. And it's very similar to what we just did. So the first thing we did in the problem just now was reading the problem carefully and figuring out what was important, right? We circled the important information that we needed. If possible, we want to identify the independent and dependent variables. So in our last problem, we weren't given the variables that we needed, so we had to kind of make them up as we went along. So if you're not given them yet, sometimes it's good to wait for a little while, although sometimes in the problems it'll say, write a function a of x, where x is, the side length, and a is the area. This past time we weren't given that. If we are, then definitely make sure you write that down right at the beginning. Next, we want to draw and label a sketch if needed. Again, sometimes they'll give you a sketch, sometimes they won't. If they don't, highly recommend drawing it out and labeling with the information that we know. Next, we want to identify the quantity that we want to maximize or minimize. It'll probably be area or sometimes volume. And we want to create a variable to represent it. Again, that is if we didn't need to before. I'm going to add that in. So create a variable to represent it if necessary, if needed. Okay, next we want to write that quantity, right? It's probably area. Most of the ones that we'll see will be area. So write area in terms of the variables, lengths and widths on your diagram. That's what we did last time, right? We wrote A in terms of x and y, right? And the area was x times y. We want to choose all but one of those variables to eliminate. The way we do that is by setting up our second equation. Remember, we used that 100 feet, right, to write a second equation about the length of the fence and how much we have. Possibly multiple equations if you're talking about volume, but most of what we'll be talking about will be area. So like in the last problem, we only needed one extra variable. Using the other, we only need one extra equation using the other given information. Then we want to solve for the variables you want to eliminate, right? So last time we solved for y so that we could get y out of that initial a equals x times y equation. And then we want to substitute into our initial equation. 7, we want to find the quantity that the problem asks for, either some value or vertex or something using precalculus if possible. Otherwise, if it's really not possible for us to do with Precalculus, then we need to use Desmos. Most of the problems that you'll see will give you quadratic equations to work with, right? And we know how to find the vertex of those. We know how to find the x-intercepts. We know how to find the y-intercepts. Those are all the different things that we're asked for typically with these types of problems. But if you're given a higher order polynomial for area or something like that, right, we know that it's more difficult to find the roots of those things or the any vertex or maximums or minimums, so we'll have to use Desmos for that. One thing that's really important here is to keep track of what variables represent and what we are looking for. So like we did in the last problem, we started at the very beginning thinking about what our independent and dependent variables were, what they represented, so that when we were working later in the problem and finding, different parts of the vertex and all of that, we were able to pretty easily think through, okay, x is a side length, which helped us be able to figure out what we were doing. So that's really important. And the last thing that we want to do here is be able to do a reality check, right, to make sure our answer is reasonable. One small math error might end up giving you something like 300. Right? If you were looking for the vertex of the last problem and you got x equals 300, we would know that that's not possible, right? Because we only have 100 feet of fencing. So something is wrong there. We want to be able to reality check throughout the problem to make sure that what we're getting makes sense. If you're getting something that doesn't make sense, then the first and best option is to try and fix it. But if that doesn't happen, then make a note that you know that this doesn't make sense, right? That could possibly get you some extra points on the test if you got some stuff wrong. Okay, now that we've looked at some steps, let's use these steps to solve another problem. So let's say we have the following. I'm gonna borrow from some pop culture here. Let's say we've got Lil Nas, and he wants to fence in some pastures for his horses. The area should be rectangular, split into 3 equal sections, by fence that is parallel to one side of the outer rectangle. He has 1,500 feet of fencing. I'm not sure what is a, super good amount of fencing for a horse pasture, but we're just doing math problems, right? So the first question here is A, find a function that models the area of the whole pasture. So again, we have a situation where we have some A value, right, area as our dependent variable, right? That's what we want the function, the value of the function to be. So area. It's going to be a second before we can figure out exactly what our independent variable is going to be. So let's do what we did next, which was draw and label a sketch. So we want the whole thing to be a rectangle, that's for sure. And it should be split into 3 equal sections by fence that's parallel to one side of the outer rectangle. So we want it to be parallel to one of the sides. I'm going to choose this side. So 3 equal sections parallel to that side. That's going to look like this, right? So what should we name these sides? I'm going to sort of deviate from the norm here, and instead of using X and Y, I'm going to use something different, maybe like S and T. So I'm going to let this side be S and this side be T, right? This whole side is going to be T. If this side is T, this whole side, then this whole side is also going to be T as well. Similarly, if this side is S, then this side is going to be S. All we need to do is figure out these lengths. But again, we know that because this is a rectangle and because these are parallel, then these lengths are also going to be S also. Okay, so let's write our function for area. Let's start it. So we know that area is equal to the length of the side times the length of the other side. So we have S and T. So A is S times T, right? Base times height. We need to get rid of one of these variables. We do that by writing another equation. What do we know? We actually I forgot to circle the important things. So important things here. Rectangular, we want to split into 3 equal sections, so that's 1. And fence that is parallel to one side of the outer rectangle. So I'm going to circle parallel to one side. And then last but not least, 1,500 feet of fencing is definitely important. We're looking for area here. So A equals S times T. We know that we have 1,500 feet of fencing total. That's what we used last time. We talked about our total feet of fencing. And then we were able to say, right, that it was X plus Y plus X. Let's do the same thing here. So how many lengths of S do we have? We have S, 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 S. So S plus S plus S plus S. How can I say that otherwise in a more succinct way? 4S, right? Similarly, I've got a length of T here and a length of T here, so we have 2T, right? It's like S plus S plus S plus S plus T plus T. Writing that succinctly looks like this. We want to solve for one of these variables. Which one seems like it might be a little bit easier? Well, T has a smaller coefficient, so maybe let's try for that one. So we want to bring 4S to the other side, so we have 2T equals 1,500 minus 4S. And we divide everything by 2, so we have T equals 1,500 minus 4S over 2. We can divide each of these terms by 2 and reduce. 1,500 divided by 2 is 750. And 4S divided by 2 is 2S. So T is equal to 750 minus 2S. That means I can replace T here with 750 minus 2S, right? I can go right up there, which means that my area is equal to S times 750 minus 2S, and that is my answer. Really quick before we move on, that means that our independent variable for this problem is S, which represents side length. Again, our units are feet and square feet. All right, part B. Find the dimensions of the outer fence that will give maximum area. This is like our part C from last time. So again, we're looking for dimensions that are maximum, right? That give us maximum. Again, with maximum, we definitely want to think vertex because we have something that is a quadratic again. So let's make our function for area look like a quadratic, right? Let's put it in standard form. Of course, it's a fine quadratic as it is, but let's put it in standard form because, right, in order to find the vertex, we need to do that negative b over 2a. So we have s times 750 minus 2s. So we distribute, we get 750s minus 2s squared. And then we write it in standard form, right, with decreasing exponents. So we get negative 2s squared plus 750s. Now we're looking for h equals negative b over 2a. So negative b, right, our b term is 750 because that's what's attached to the s term. And our a is negative 2. Negative 750 divided by negative 4 is 187.5. What does this represent? Well, this is the s value that gives maximum a, right? So 187.5 feet is going to be the s value that makes this the maximum area. In order to find the dimensions, right, we need both the s and the t. So we need to find t here. Again, we're in a situation where we know what t is equal to in terms of s. We've already found that, right, in order to do this substitution. So t is equal to 750 minus 2s, right? T equals 750 minus 2s. So when s is 187.5, that means we're looking at 750 minus 2 times 187.5 is 375? 750 minus 375 is 375. And that's our t value. So we have 187.5 by 375 feet. Okay, last but not least, what is the maximum area for the pasture? Well, we know that area we know what area is as a function of s, right? It's a equals s times 750 minus 2s. And we know that the s value that's going to give us the maximum area is 187.5. So let's just plug that in, right? So 187.5 times 750 minus 2 times 187.5 gives us 187.5 times 750 minus 2 times 187.5. That sounds familiar. Haven't we done this already? Yes, we have, right? We found the y value here, 375. So we actually could have just multiplied these together, right, to find the area, right? All of this is interconnected. There's no one method for solving. We can use all of the information in whatever way we want to. Some ways are faster than others. Some ways are more efficient. But there's no one correct way to solve. So when we multiply these together, we end up with an area of 70,312.5 square feet. And that's the answer. Okay, one last problem I would like to look at. This one is from the lab manual. And this is number 2, again from the section Polynomial Modeling. I'm going to copy it here. Okay, so we've got a wire, and that wire is 10 centimeters long, and we cut it into 2 pieces. We cut one piece that's length x, and then of course, since we had 10 to start with and we've removed x, then we have 10 minus x left over. And one of those pieces is bent into a square, and the other is bent into a circle. So our first step here, or question that we're asked, is to write a function that models the total area enclosed by the 2 figures Okay, so a lot going on here, right? Let's find the important information first before we get started. So first of all, the wire is 10 centimeters long. That's definitely important. We've cut it into 2 pieces. One has length x, and the other is 10 minus x. One piece is bent into a square, and the other piece is a circle. That's all the important parts of the information that we're given. A function that models the total area, right, is what we're looking for. So total area enclosed by the 2 figures. So again, let's, as always, start with our sort of point. We're again looking for area. I'm going to call it big A. Area. And this time we're actually given an independent variable, right? They told us that we're working with x. We know that x is the first cut, right? And since it's a length, and we already know that the length here is in centimeters of the wire, then we're going to be working in centimeters, which means that the area is going to be square centimeters. Okay, let's draw a diagram. I'm going to draw this one pretty big. So that's our wire. And we've cut it, I don't know, I'm just going to say there. So the whole thing all together is 10 centimeters. This length is x centimeters, and this length is 10 minus x centimeters, right? It's what's left over. We took this first part and we bent it into a square. Right, so that wire looks like this now, that part. And I'm gonna draw a little niche in it so we know, that's where it starts and that's where it ends. And this one, we did the same thing, but we made it into a circle. And again, I'll make another little niche in it so we know where it ends. What do we know here? Let's start with this square. So we know that this length, right, the length of this piece of wire is x. So all the way around is x. If the whole way around is x, again, remember we're looking for area. What is the area of a square? I'm going to denote this as A1. I'm going to call this A1. The area of a square is, well, for a rectangle it's base times height. For a square, it's still the same thing, but the base is the same as the height, right? So we are actually just one side, whichever one, squared. So if we need to figure out what the side is squared, we need to find the side. What is one of these side lengths? Well, if the whole perimeter, right, side plus side plus side plus side is x, then one of those sides is going to be what? Well, it's 1/4 of the whole, right? We've got four sides make the perimeter. So 1/4 of the perimeter, which is x, is going to be a side. So side squared is going to give us x over 4 squared. Okay, let's do the same thing for the circle. What do we know about the area of a circle? I'm going to call this A2. Let's sort of refresh on our circle formula stuff. Well, the area of a circle is pi r squared, right? The other important thing that we always talked about was circumference, right? Circumference is 2 pi r. All right, so if area is pi r squared, that means we need to figure out what r is, right? Radius is this guy. Do we know that? Definitely not yet. What do we know? Well, we know that the length around the outside, right, which for a circle is called circumference, is 10 minus x, right? That's the length of the wire. If the circumference is 10 minus x, then we can find r, right? So this is some extra stuff for circle. We know we have 10 minus x for the circumference is equal to 2 pi times r. We need to find r, which means we can just divide this stuff to the other side, right? So that gives us r equals 10 minus x over 2 pi. Then we know that the area is pi times r squared, so that means that A2 is equal to pi times what we just found for r, right? We want to substitute in there 10 minus x over 2 pi squared. So that means the area, remember we're looking for total area enclosed by the two figures. The area for the total area enclosed is going to be the sum of the two individual areas, so that's A1 plus A2. We know that A1 is just x over 4 squared, and that A2 is pi times 10 minus x over 2 pi squared. And that's our answer. right? This is a function for area. What is the domain of this function? Well, domain is the collection of possible input values. Our input variable here is x. So what are the possible values for x? Let's look at our initial diagram. So we have this wire, it's 10 centimeters long, and x is the length where we cut the wire. So it can be anywhere along this length, right? Which means it can be anywhere between 0 and 10. However, we know that we cut it into 2 pieces, right? So if we cut at 0, that doesn't do anything, right? If we cut exactly at 0, we've basically just put the scissors or, wire cutters, whatever you're using, at the end of the wire and not done anything. So in order to cut it into 2 pieces, it needs to be anything bigger than 0, and then again, similarly, anything smaller than 10. So the domain of this function is 0 to 10. Last but not least, determine the value of x that minimizes the area. Okay, so we're looking for, this time, x. And again, we're looking to minimize the area. So this equation here is really funky, right? We've got a lot going on. We've got a bunch of pi, we've got just some messy stuff happening. So for this equation, we are going to use Desmos instead of solving this using quadratic stuff. You will not see something like this that's this difficult even on WebAssign. You do have a problem that's very similar, except the second part is actually bent into a square as well. So they're both bent into squares, but we've seen how to do that for one, so we can do that for another. That's totally fine. But, for this one, this is not like something you would see on a test. Of course, on a test, you won't have something that you'll have to use Desmos for because you're not allowed to use Desmos on the tests. So you'll be given something that you can solve using your knowledge of quadratics and that sort of thing. So again, for this one, let's just use Desmos and we'll look at it to see what the minimum value is and figure it out from there. If we look at Desmos, we get the following function. Looks like this. We plugged all of this in into the desmos.com/calculator. If we look at it, we see we have that point that gives us a minimum value. We want to pick, right? Of course, we want to make sure that it's within our domain and all that stuff, all that good stuff. This is between 0 and 10, so this is good. We end up getting an x value, right? Of course, we're looking for the value of x, of 5.601. And what are the units on that? Centimeters. And that is our answer. Okay, so hopefully this is making sense. Polynomial modeling isn't the easiest, but once you sort of see what's going on and get the hang of it, all the problems are very, very similar to each other. It's just a matter of being able to set them up. Of course, with word problems, we want to remember not to get too intimidated by it, and that the most important part is really just to be able to kind of convert in our brains from words to math and vice versa. Okay, that's all I have for y'all today. Thanks for watching.